Welcome back. Last week, we assembled the machine's core framework, its computational architecture. This week, we give it a brain. We are installing its logic engine, the very system that will empower it to calculate, to reason, and to make intelligent decisions.
So here's our mission plan. We'll begin by building that logic engine from the ground up. Then we'll master our arithmetic tools and learn how to manage data with professional precision. From there, we dive deep into the core of all decision-making, and we'll wrap up by instilling the engineering mindset that separates the amateurs from the architects.
All right, let's get into it. Think of week one as building the hardware. We put together the chassis, the motherboard, all the physical components. Now, today, we are installing the operating system. We're building the logic engine that allows this machine to actually think.
And the fundamental building blocks of that engine are operators. Now, these might just look like simple symbols on a screen, but don't be fooled. They're the gears, the circuits, the very heart of your program's logic flow. Mastering them isn't just important, it's everything.
The first set of tools we're going to install in our logic engine are the arithmetic operators. Now, this is where we teach the machine basic math, but trust me, we're going to approach this from a much higher, much more powerful perspective.
I really want this to sink in. These symbols you see here, they're not just for adding up numbers. In the hands of an engineer, they become precision instruments for carving up data, for finding hidden patterns, and for making sense of incredibly complex systems. That's their real power.
So here's our arithmetic toolkit. You've got your standards: addition, subtraction, multiplication. They do exactly what you'd expect. But where the real professional-grade work gets done is with the last two on this list, modulus and floor division. These two are your secret weapons.
Let's make this really simple. Imagine you have 5 apples and 2 boxes. Floor division, or 5//2, tells you how many full groups you can make. The answer is 2. You can put 2 apples in each box. Modulus, or 5% 2, tells you what's left over. The answer is 1. You have 1 apple remaining. One operator gives you the whole groups. The other gives you the remainder. This is the foundation of advanced data partitioning.
All right, now that our machine can calculate, let's talk about writing code with professional polish. It's not enough for code to just work. It needs to be clean, efficient, and elegant. And that starts with how you handle assignments. You'll see this everywhere. And yes, technically it works, but this is verbose. It's a two-step command. First, read the value of x and add 5, and then, in a second step, assign that new value back to x. It's not the professional way.
This is the professional standard. X plus equals 5 is one clean, single compound operation. You are telling the machine directly, modify the value of x by adding 5. It's faster, it's more readable, and it is the undisputed standard in any serious coding environment.
And of course, this principle of efficiency applies across the board. Whether you're adding, subtracting, or multiplying, using these compound operators is a clear signal that you understand how to write concise, professional code. It's a small detail that says a lot. Okay, let's move to the main event. We have tools to calculate and manage our data. It is now time to give our machine the power to make its own intelligent decisions, and we do this with relational and logical operations.
Every single piece of modern software, from your phone's operating system to the guidance system on a rocket, is built on this one simple concept: Boolean evaluation. Every complex decision boils down to a series of simple questions with only one of two possible answers: true or false, yes or no, 1 or 0.
These are the tools we use to ask those questions, the comparison operators. Their only job is to compare two values and then return a Boolean result, either true or false. Is the temperature greater than 30? Is the password entered equal to the one on file? These are the questions that drive our logic.
But what happens when one question isn't enough? That's where our logical operators come in. And, or, and not are the tools we use to combine the answers to multiple questions, allowing us to build a single, complex, and incredibly precise condition. This is how sophisticated logic is born.
Let's look at a real-world logic flow, like authorizing a user. First, the system asks a question: is the user's access level greater than 5? That's a true or false. Then it asks a second question: is the user's login status currently true? By combining these two with an AND operator, the system can make a final intelligent decision. Access is only granted if the answer to both questions is true.
This brings us to our final and, frankly, our most critical point today:
You can have all the tools in the world, but they are useless without the right mindset. We are not here to be coders. We are here to be engineers.
Remember this: anyone can learn to write lines of code. An engineer, however, architects the solution first. They design the logic flow, they consider the edge cases, they build a robust blueprint before a single line is written. This is the mindset I expect you to bring to your logic map presentation.
So I'll leave you with this question to reflect on. Are you just a coder, someone who simply writes instructions to make something work? Or are you an engineer, someone who designs elegant, efficient, and powerful logical systems? The choice is yours.